Okay, get ready because we're about to do a very nasty conjecture. The thing that's tricky about this is spotting what the conjecture is, and then we're going to try and prove it using induction. I'm really going to encourage you to pause the video and try and work as far as you can on this problem before unpausing and seeing how it's done. Really important you try and do that to get the most out of it. Okay, so if you know how to do part A, please pause and try. If not, I'll show you how part A works. A is a matrix, a squared is 2a plus 3a, and then we can work out a cubed. So for this bit here, a cubed, we can write this as a times a squared. So this is a into 2a plus 3i. This is 2a squared plus 3ai. Now, that just becomes 3a on the end because a times I is a. That's what the identity matrix does. And this will be 2. Now I'm going to call this thing star. A squared is 2a plus 3i, just like that. So that's using star, just like that. Okay, if we expand this in, that's 4a plus 6i plus 3a. So that becomes 7a plus 6i. All right, wonderful. Now, if you watch a cubed, make sure you pause the video and try a to the 4 and a to the 5, etc. All right, here's how that one's done. A to the 4 is a times a cubed. We can use our previous answer, so that's a into 7a plus 6i. That becomes 7a squared plus 6ai. That's going to be 7 into the thing we had for star. So a squared is 2a plus 3i. And 6ai, so that's 6a. So that's using star, and the fact that the identity matrix times any matrix gives you that matrix you started with. That's 14a plus 21i plus 6a, and it appears that that is 20a plus 21i. Make sure you pause the video and try a5 if you haven't done that already, but I'll show you how that one works. A to the 5 is a times a to the 4. That's a into the answer we just got for a to the 4 was 20a and 21. That should be an I. Okay, 20a plus 21i. That becomes 20a squared plus 21ai. That's 20 into a squared is 2a plus 3i. And 21ai is 21a. So that's 40a plus 60i plus 21a. That should give us 61a plus 60i. Okay, now at this point, I'm hoping that you see that there may be some pattern going on, but may have trouble spotting what that pattern is. And it is a very difficult pattern to spot. You would not know the formula just by looking at it. But what I'm going to show you in this video is a process for finding that formula if you have a rough idea of maybe what it is. So let's look at the n value. And let's look at the coefficient of a in a to the power of n. Okay, so if n is 2, then we're looking at a squared. So that number would be 2 in front of the a. If n is 3, we're looking at a cubed, so that's 7a there. So the next one across should be 7, then 20, and then 61. And so on and so forth. Now that I've got this table, again, pause the video and really try and spot the pattern here. Well, not spot the pattern, but see if there's a way that you can work out what the pattern's going to be. Okay, I'm hoping if you had a look, we may be able to spot some kind of, it looks like it's sort of timesing by 3 maybe. In particular, the a and the i's are always 1 apart. And you can hopefully see that 7 times 3 is 21, 20 times 3 is 60, and so on and so forth. that is true, that pattern works. So in general, we'd really like it if we could just directly times by 3 down this table. Now, that actually doesn't work. 2 times 3 is 6, not 7. But if I do 2 times 3 and add 1, I do get 7. 7 times 3 should be 21. It's 20. So I'm not going to be adding 1 again, but I am going to be taking 1 this time. 20 times 3 is 60. There we go, times 3 plus 1. And if you can see the pattern here, then we're timesing by 3 and taking 1 to get the next term. So the next term I would predict might be, well, 61 times 3, that's 183. Take 1. So 182 for the A value. It turns out that is actually correct. Yeah, and you can work that out with the matrices. So that's the general pattern here. We call this a recursive formula. And the reason for that is, well, like it gives you the next term given the previous term. It doesn't just give you any term that you want. We would like to get, so we've got recursive, we want an explicit formula. We'd like to get just a general formula. Okay, pause the video, try and get your explicit formula, really important. Anyway, here's how it's done. So basically, if n is 2, we're just going to be starting with 2, so that's good. If n is 3, well, we're going to be doing 2, we're timesing that by 3, and we're adding on 1. If n is 4, well, we're going to take the result that we just got from n equals 3. So that was 3 into 2 plus 1. But then I need to times that entire answer by 3 and take 1 from that. So really, we've done that step there. Have a think about why that's true before you move on. Very important. You have your head around that process of recursive stuff. And we can expand this out. So that would be 3 squared into 2 plus 3, take 1. Okay. So that is n equals 4. To get n equals 5, I'm going to be taking that term that I just got from n equals 4. So that's 3 squared into 2 plus 3, take 1. And I'm going to be timesing it by 3. And because I'm going to the 5th term, I'm going to be adding 1 this time. And we can FOIL that in. So that is 3 cubed into 2 plus 3 squared, take 3 plus 1. That's n equals 5. And one more for good measure, n equals 6. So I'm going to take that thing that I just got for n equals 5. And I need to times it all by 3 and take 1. So if we FOIL that in, that's 3 cubed into 2 plus, that should have been a 3 there. My bad. So it's 3 to the 4 into 2. Plus 3 cubed, take 3 squared, plus 3, take 1. And I'm hoping we can see the pattern that's starting to form here. Pause the video, try and figure out what the actual formula is based off this pattern. Okay, hopefully you've had a try. We need to break this expression into 2 pieces. So in general, for n equals any value, it looks like it might do this. 3 to the power of n take 2 times 2 plus 3 to the power of n take 3 take 3 to the power of n take 4 plus 3 to the power of n take 5 all the way down to, now depending exactly how these powers play out, you're going to get plus or minus 3 to the 1. Well, let's go like 3 squared, then 3 to the 1, then 1. And they sort of flip. I don't know exactly how those last few terms are going to play out, but that's pretty much what they do. Okay, so that's generally what we've got. I'm going to call this thing here S of n take 3. The sum of, actually no, I'm just going to call it S for sum. And it's a geometric sequence. So if we look at this geometric sequence, we can call this term here T1, this term here T2, that term is T3, and it goes all the way up to these last couple terms. This is T of n take 2. There are n take 2 terms in total, because that one there is sort of 3 to the 0, so sort of n take 2. This is T of n take 3 here, just like that. Okay, so we need a sum for a geometric sequence, which conveniently I prepared before. There's a formula, and this comes from year 11 spec. T1, Rn take 1, and R take 1. So we need to identify T1, R, and the number of terms that we're looking at. So T1 is 3 to the power of n take 3. That's helpful. R is what we're timesing by each time. Now, if you think about it, like 3 to the n take 3 times by what gives us that next term, minus 3 to the n take 4. That number there essentially has to be, well, if you want to add the powers together, it should be 3 to the power of minus 1. But you also want to introduce a minus, so something like that. This is minus a third that you're timesing by to get to the next term. So each time we go forward a term, we're timesing by minus a third in this sum. Have a think about why that's true, but it is. All the way down to 1. So that's our R value is minus a third. And the number of terms, we sort of discussed it here, but it's n take 2 terms. So now we can plug everything into our formula. And that formula was T1 R to the n take 1 over R take 1. So that would be S is T1 R to the n take 1 over R take 1. Okay, now our geometric formula would normally have like n in it, but we don't want it to be n necessarily. We want it to be, I'm just going to call this thing x up here. X is the number of terms, which is n minus 2. So you're going to be really careful about that with this formula. But now let's plug in everything we know. So T1 is 3 to the power of n take 3. This will be R, so minus a third to the power of n take 2. Take away 1, all over R take 1, so that's minus a third take 1 there. This is 3 to the n take 3 minus a third to the power of n take 2, take 1, all over, now this is minus 4 thirds on the bottom there. Now when you're dividing by 4 thirds, that's like timesing by 3 quarters, so I can actually pull the 3 up the top here. So 3 into 3 to the n take 3 minus a third to the n take 2, take 1. All over minus 4, just like that. And that will just become 3 to the power of n take 2 up the top, minus a third to the power of n take 2, take 1, all over minus 4. Next thing I'm going to do is FOIL the 3 to the n take 2 in, so that'll go in like that. So that would be 3 to the n take 2 times minus a third to the power of n take 2, minus, and then we want to FOIL the 3 in there. So that would just become 3 to the n take 2, all over minus 4. Now this is why I'm really keen on this conjecture. It works out really nicely because they're the same powers on these first 2 terms. So this just becomes 3 times minus a third to the power of n take 2, both together. 3 times minus a third is minus 1. So that's minus 1 to the power of n take 2, take 3 to the n take 2. And then what we can do is get rid of this negative on the negative 4. So maybe with this minus 4, change that to a plus 4 down the bottom. But then we have to flip the top as well. So that's minus 1 to the n take 2, plus 3 to the n take 2. And if you want, you can actually flip the 3 to the n take 2 first. This would be negative 1 to the power of 1 and negative 1 to the n take 2. So you can just add those powers with a plus there. So that's 3 to the n take 2 plus negative 1 to the n take 1. So that's S. Now, S is the sum of that big sequence there. That's what I've called S. I'm going to call this other thing right at the start just E. For the extra bit, I suppose. So the total would be E plus S. So total E plus S. So E was 3 to the n take 2 times 2. And then S is this whole geometric thing. So 3 to the n take 2 there, plus negative 1 to the n take 1. So if we want, we can cross multiply this. So this is 3 to the n take 2 times 4 over 4. And then 3 to the n take 2 plus negative 1 to the n take 1 all over 4. And then that would help us get it all over a common denominator of 4. So this is 8 lots of 3 to the n take 2 plus 3 to the n take 2 plus negative 1 to the n take 1. And then we can combine like terms. So the first two terms are like terms on the top of this fraction. We got 9 times 3 to the n take 2. And conveniently, 9 is also 3 squared. Okay. Now, conveniently, we can add the powers as well. And you can see why I'm really liking this conjecture. Because all the algebra works out really nicely. So that should be our total. And apparently, that's supposed to be the coefficient of A on our induction. So pretty much, you're not going to spot that conjecture. It's really tricky to spot. But what I'm hoping you can do is a process somewhat like this to spot the pattern with those numbers. In our case, it was a power, but sometimes, for example, if you think it might be a quadratic or something as a pattern, you could actually try like ax squared plus bx plus c, and then use the first 3 equations to find those 3 unknowns and see if it's a quadratic. In our case, that wouldn't work, but you could do that as a general process. Okay, so my claim is that the sum is supposed to be this lovely expression here. I happen to have that graphed. And let's check. So if we plug in various n values, I should get various coefficients of A. So for example, if I plug in 2, I get 2. If I plug in 3, I get 7 on the y value there. Hopefully we can see that. If I plug in 4, I'll get 20. And if I plug in 5, I'll get 61. Apparently the next one was supposed to be 182. So 6 looks to be 182 as well. So there's our conjecture proven. At this point, I'd really encourage you to try and figure out what the I value should be based on the coefficient of A. Anyway, hopefully you've tried that. So we can just say, therefore, A to the power of n is. Now, with the A term, we've got a conjecture for that already, and then we've just got to think about what the I term is as well. So the conjecture that we got was 3 to the n minus 1 to the n take 1 over 4. So that's the value that should go with A. And with the I term, it looks like sometimes it's 1 less and sometimes it's 1 more. So it looks like if A cubed, so that would be an odd power, then it's 1 less than the A value. But on the even power, it's 1 more than the A value. So let's see how that all plays out. Okay, so it looks like it should be 3 to the n plus negative 1 to the n take 1 all over 4. Now, I'm just going to put plus or minus 1 here. So I'm going to say plus 1 if n is even. And it's minus 1 if n is odd. Which I think was the correct way to go about it. Yeah, it was. Okay, so a really convenient way is to just make this plus -1 to the power of n, because that will force it to be what we need. If n is odd, that becomes -1, and if n is even, that becomes +1. So hopefully we can work through some of this algebraically and see if we can work out a nicer way to put this. So that would be 3 to the n plus -1 to the n take 1 all over 4 plus 4 lots of -1 to the n all over 4. So we're cross multiplying. So that's 3 to the n plus -1 to the n take 1 plus 4 times -1 to the n all over 4. So that should be, let's see if we can maybe pull out a common factor of -1 to the n take 1. What we're left with is 1 and 4 times -1, just like that. Okay, so that would be 3 to the n and then -1 to the n take 1, and that would be -3 inside the brackets all over 4. So this would be 3 to the n take 3 times -1 to the n take 1. I don't really like it being double take, so maybe I'll pull this -1 into the power as well. So 3 to the n take 3, and then that should be -1 to the n all over 4, and plus 3. That should be -1 to the n. We could factor out a 3 on the top, but I don't really want to. So that's what this ends up being. So the final conjecture, and you can see why I said this is a tricky conjecture. So this is 3n plus -1 to the n take 1 all over 4 times a plus, and then this is 3 to the n plus 3 into -1 to the n all over 4 times I. Okay, I'd encourage you to pause the video and try and prove that conjecture using induction. Okay, let's look at the proof. Okay, let Pn be the statement. Now that statement is going to be this exact thing again. There it is. So we're going to start from P2. Okay, so on the left-hand side, we're going to get a squared. We're sort of given what a squared was in this question. So 2a plus 3i. And on the right-hand side, well, so 3... All right, maybe I'm just going to put it out like this. The a coefficient is going to be 3 to the 2 plus -1 to the 2 take 1 all over 4. This is 9 plus -1 to the 1 all over 4, so that's 8 over 4, which is 2. So yes, good, that matches. And for the I coefficient, that's going to be 3 to the power of 2 plus 3 times -1 squared all over 4. This is 9 plus 3 times 1 all over 4. This is 9 plus 3 over 4, which is 12 over 4, which is 3. So it looks like the 3 matches with the 3i as well. Okay, assume. Oh, by the way, we start this induction from P2 because we don't actually, well, we might be able to start it from 1, but we've only developed this conjecture from n equals 2 because we don't really have the A matrix. I guess A would be 1a plus 0i, which I think still follows the pattern. But yeah, we'll see how we go. Actually, I wonder if that extends to negatives. That could be a really interesting way to do this. Anyway, we're just going to start from 2. So I'm just going to say for rule n greater than or equal to 2 to make it simple enough. Well, simple is a stretch. So we're going to assume pk. So we're going to assume that all this is true, just replacing n with k. So a to the k is 3 to the k, k take 1, 3 to the k, and ki. All right, good. So let's look at pk plus 1. Okay. A to the k plus 1 is a to the, well, a times a to the k. I probably still want to show over here before we launch into it, see exactly what we want. Want to show is like your right-hand side, and it's also like the right-hand side, but instead of k's, you've got k plus 1s. So on our right-hand side, we're going to have 3 to the k plus 1. That's minus 1 to the k there. 3 to the k plus 1 and plus 1 in there. So hopefully that should all play out nicely. Let's see. Might simplify down more, I'm not exactly sure, but we'll find out. So this is a into 3 to the, well, it's into all that stuff. From, now I'm going to call this double star because I think I used single star before. Okay, so this is 3 to the k plus negative 1 to the k, take 1 over 4. A squared, because we FOIL the a in. And then we're going to FOIL the a in there for the I. So that is 3 to the k plus 3 lots of negative 1 to the k over 4a. So in theory, that should match. Anyway, let's keep going. So let's put in what a squared actually was. So 3 to the k, negative 1 to the k take 1 over 4. Now, a squared was supposed to be 2a plus 3i. So let's see if we can figure that out. 2a plus 3i. Okay, and then over here, 3 to the k plus 3 lots of negative 1 to the k over 4a. Still sits there like that. And now we can sort of FOIL this all in nicely. So that is going to be, I'll keep everything over 4 first of all. Let's think about the a term. So what I might do is I might actually just group the a's together now. So the a term will be 2 lots of 3 to the k plus negative 1 to the k take 1 all over 4. And then this other a term that we had here. So that was 3 to the k, 3 lots of negative 1 to the k all over 4, just like that. So that's the a term. The I term is going to be a bit simpler. It's 3 into 3 to the k plus negative 1 to the k take 1 all over 4i. And I will underline in green just so we got it all together. All right, let's simplify down. So this will be 2 lots of 3 to the k plus 2 lots of minus 1 to the k take 1 plus 3 to the k plus 3 lots of negative 1 to the k all over 4 times by a. And then the I term is going to be, well, we can FOIL the 3 in. So that's 3 to the k plus 1 on that. Plus 3 into minus 1 to the k take 1 all over 4 times by I. Okay, so now we've got to group like terms on the left. So this will become 2 lots of 3k plus 3k. So that's 3 lots of 3k. Then it's 2 into minus 1 to the k take 1. So let's just draw those out together and think about how they might go in together like that. All right, so I'm actually just going to leave it like that for now. Then we'll deal with it in a second. Okay, 3 to the k plus 1, and then 3 times minus 1 to the k. I suspect this last term might already be matching I want to show. Let's see. Well, it does, in the sense that minus 1 to the power of k plus 1 is the same as minus 1 to the... Yeah, because minus 1... is 1. So if you bump up the power by 2, it doesn't change anything. Okay. And then over here, we're supposed to get some nicer terms here. So I'm going to write this here as minus 2. And then the minus 1 power sort of goes up or down by 1 because I pulled out one of the minus signs. And then we can group like terms here. So 3 to the k plus 1. And then that is plus 1 times negative 1 to the k, all over 4, a. And then this term, we already had what we wanted. And I reckon that is the proof. Therefore, pk plus 1 is true. Therefore, by induction. And then we can pull this thing from up here. That is true for all n in Z with n greater than or equal to 2. What a wonderful proof that one is. And there's a whole lot. Now, the point of this all is, hopefully this helps you spotting conjectures. So you may not see a pattern, but we can use tools like geometric sequences and stuff to get what the conjecture is.